There is a machine in Hefei, China, that is hotter than the core of the sun, not slightly hotter, 7 times hotter. The plasma inside it, a superheated cloud of hydrogen atoms stripped of their electrons, moving so fast that they fuse together and release energy, reaches temperatures of over 100 million degrees Celsius. The surface of the sun is approximately 5,500 degrees Celsius. The core of the sun, where the same fusion reactions occur naturally, reaches about 15 million degrees. The machine in Hefei runs 7 times hotter than that. And in January 2025, that machine held its plasma at that temperature for 1,056 seconds. 17 minutes and 36 seconds of continuous fusion conditions, not a flash, not a pulse. A sustained, controlled, monitored burn that lasted longer than any fusion plasma in history, by a margin so large that the previous record was not even close. The previous world record was 390 seconds, set by the same machine in 2023. The new record did not nudge it forward, it nearly tripled it. For 60 years, nuclear fusion, the reaction that powers the sun and every other star in the universe, has been the energy technology that is always 30 years away. Always promising, always funded, always the subject of optimistic research papers and cautious progress reports, and always somehow not quite ready. The 1,056-second result from the East Tokamak in Hefei does not mean fusion power is ready tomorrow, but it means something important changed. And understanding what changed and why 1,056 seconds is different from 390 seconds in a way that is more than arithmetic is what this video is about. My name is Addy Mel. Subscribe right now and hit the like button if you want to understand the technologies that are actually moving the needle on the world's hardest problems. Turn on notifications. We find one of these every week. This one has been building for 60 years. Let us start with what fusion actually is and why it has been so hard. Every joule of energy produced by the sun, every photon of light that has ever warmed the Earth's surface, driven the water cycle, powered photosynthesis, and ultimately made life possible, comes from the same basic process. 2 atomic nuclei, moving fast enough and close enough, overcome their natural electromagnetic repulsion and fuse together into a single heavier nucleus. The mass of the product is slightly less than the combined mass of the 2 nuclei that fused. That missing mass is converted directly into energy, following Einstein's equation. A very small amount of mass becomes a very large amount of energy. In the sun, the fuel for this reaction is hydrogen, the simplest and most abundant element in the universe. The sun fuses hydrogen nuclei into helium, releasing energy at every step. It has been doing this for approximately 4.6 billion years and has enough fuel to continue for another 5 billion. The scale of the energy release from this reaction is what makes stars shine with the brightness they do across the vast distances of space. On Earth, the most practical fusion reaction uses 2 specific isotopes of hydrogen. Deuterium is abundant. It can be extracted from seawater, where it occurs naturally as a small fraction of all hydrogen. Tritium is rarer and must be produced, but it can be bred from lithium, which is itself reasonably abundant. The fuel for a fusion power plant, in principle, is seawater and lithium. The energy density of the reaction is approximately 1 million times higher than burning natural gas. A fusion power plant running on deuterium extracted from a bathtub of seawater would produce roughly the energy equivalent of burning 300 liters of petrol. The product of the deuterium-tritium fusion reaction is helium, an inert, harmless gas, and a high-energy neutron. No carbon dioxide, no sulfur dioxide, no long-lived radioactive waste of the kind produced by fission reactors. The neutron does activate the materials of the reactor over time, creating some radioactivity, but this decays to safe levels within decades rather than the thousands of years associated with fission waste. Fusion is not perfectly clean, but it is dramatically cleaner than any other energy source capable of. The reason fusion has been so hard to achieve on Earth is the temperature required to make the reaction happen. In the sun, fusion occurs at 15 million degrees Celsius. At that temperature, hydrogen nuclei have enough thermal energy to overcome their electromagnetic repulsion, often enough that fusion reactions occur at a useful rate. But the sun can do this at 15 million degrees because its enormous gravity holds the plasma together. The weight of the star itself provides the confinement that allows fusion to proceed. On Earth, there is no gravity large enough to confine a plasma. And paradoxically, making fusion work on Earth requires higher temperatures than the Sun achieves, around 100 million degrees, because without gravitational confinement, the plasma must be at such high temperature that the fraction of collisions energetic enough to fuse is high enough to sustain the reaction. The plasma must be confined by other means, and at 100 million degrees, no material on Earth can contain it by physical contact. The solution that has been pursued since the 1950s is magnetic confinement. Strong magnetic fields, generated by superconducting electromagnets, can hold the charged particles of a plasma in a confined region without any physical contact between the plasma and the reactor walls. The geometry most commonly used, a torus, like a donut, gives the plasma a path along which it can circulate continuously, while the magnetic field prevents it from touching the surrounding structure. This device is called a tokamak, from the Russian acronym for its description. The challenge of tokamak fusion is maintaining the plasma, keeping it hot enough, dense enough, and confined enough to sustain the fusion reaction for long enough that the energy produced exceeds the energy put in to create and maintain the plasma. This ratio, called Q, needs to be greater than 1 for break-even and much greater than 1 for a practical power plant. Achieving Q greater than 1, sustaining the plasma for useful durations, and doing both simultaneously has been the challenge that has kept fusion 30 years away for 6 decades. The experimental advanced superconducting tokamak, EAST, is not the largest fusion device in the world. That distinction belongs to JET in England and will soon pass to ITER, the international fusion project under construction in France. EAST is not the most powerful in terms of plasma current or magnetic field strength. It is not designed to achieve Q greater than 1. It is an experimental device, not a power-producing prototype. What EAST is designed to do, and what it does better than any other fusion device in the world, is run for a long time. Most tokamaks operate in pulse mode. They create a plasma, sustain it for as long as their engineering allows, and then the plasma terminates, either because some instability grows large enough to disrupt it, or because the energy injection system that heats the plasma cannot run continuously, or because the copper electromagnets that create the magnetic field overheat and need to be switched off. Pulse durations of seconds to minutes have been typical. The physics of the plasma can be studied in detail during these pulses, but the engineering of steady-state plasma, what happens to a fusion plasma and the systems around it when it runs not for minutes but for hours, cannot be studied in a machine that only pulses. EAST was built to study steady-state plasma. Its superconducting magnets, the key feature that distinguishes it from earlier tokamaks, can run continuously without overheating because superconductors carry electrical current without resistance and therefore without generating heat. The plasma heating systems, combinations of radio frequency waves and neutral beam injection that add energy to the plasma to maintain its temperature, are designed for extended operation. The plasma-facing materials and the diagnostic systems are all engineered for the thermal loads and radiation environment associated with long-duration plasma operation. The institute that operates EAST, the Institute of Plasma Physics under the Chinese Academy of Sciences, located at the University of Science and Technology of China campus in Hefei, has been running plasma experiments on the device since it was commissioned in 2006. The progress since then has been systematic, documented, and shared with the international fusion research community through publications and through the collaborations that are standard in fusion science. The 390-second record set in 2023 was itself a major milestone, the longest sustained fusion plasma in history at that point, achieved by combining advances in plasma control algorithms, improvements to the plasma-facing components that manage the heat load from the plasma edge, and refinements to the heating system operation that maintain the plasma temperature more stably across long durations. The 1,056-second result in January 2025 built on all of those advances and added several more. The plasma temperature was maintained at over 100 million degrees Celsius throughout the 1,056 seconds, not varying significantly above or below that value, which requires active control of the heating power input to compensate for the energy losses that occur continuously as the plasma radiates and as particles escape from the magnetic confinement. Maintaining temperature stability across 17 minutes of plasma operation requires a control system that responds faster than the timescales on which plasma instabilities develop, milliseconds to seconds, and that does so continuously, without human intervention, using measurements from the plasma diagnostic systems to adjust the heating power in real time. The plasma current, the electrical current flowing around the torus inside the plasma, which is what generates the magnetic field component that provides confinement, was maintained at approximately 1 million amperes throughout the run. Sustaining this current requires continuous injection of radio frequency power to drive the current non-inductively, a technique called current drive that is essential for any tokamak aiming at steady-state operation, because the inductive method of driving plasma current that most tokamaks use cannot run continuously. The previous record was 390 seconds. The new record is 1,056 seconds. In raw numbers, the improvement is impressive but not qualitatively transformative. A factor of 2.7 is significant progress, but it is the kind of progress that a research program makes by incremental improvement over years. What makes 1,056 seconds different is not the number itself. It is what happens to the physics of the plasma at that duration. Plasma physicists have a set of problems that they know occur in long pulse operation, but that shorter pulses are too brief to fully develop. These are called steady-state plasma problems, and they are distinct from the instability problems that dominate short-pulse fusion research. In a short-pulse plasma, the dominant concern is preventing the plasma from disrupting, from suddenly losing its confinement and terminating in a fraction of a second. In a long-pulse plasma that has been stabilized against disruption, different challenges emerge. One is the accumulation of impurities. The plasma interacts with the walls of the vacuum vessel that surrounds it, not through direct contact, since the magnetic field prevents most of the plasma from reaching the walls, but through the edge region where plasma particles escape the confinement and hit the wall surface. These interactions erode small amounts of wall material, which enter the plasma as impurities. Impurity atoms, heavier than the hydrogen isotopes that are the fuel, radiate energy much more efficiently than hydrogen, cooling the plasma. If impurities accumulate, they can cool the plasma below the threshold at which fusion reactions occur, effectively quenching the reaction from the inside. Managing impurity accumulation requires a combination of material choices for the plasma-facing components, materials that erode slowly and whose erosion products are tolerable in the plasma, and active control techniques that can detect impurity buildup and either slow the accumulation or drive impurities out of the plasma. In a 390-second plasma, impurity accumulation is present but manageable with existing techniques. In a 1,056-second plasma, the impurity dynamics are fully developed. The plasma has had time to reach a genuine quasi-steady state in its interaction with the wall, and the control techniques required to maintain plasma purity across this timescale are tested in a way that shorter pulses simply cannot test them. EAST's success in maintaining a clean, hot plasma for 1,056 seconds means that the impurity control techniques developed by the Hefei team work at the timescale that matters for a real power plant. A fusion power plant will not run for seconds or minutes. It will run for months between maintenance shutdowns. The physics must work at hour and day timescales, demonstrating that the plasma control techniques work at 17 minutes, not in every detail of a power plant, but in the fundamental plasma physics, is a qualitatively different validation than demonstrating they work at 6 minutes. Another steady-state problem that fully manifests at long durations is the heat load on the diverter, the section of the tokamak that handles the exhaust of particles and energy from the plasma edge. In a short pulse plasma, the diverter sees a high heat load for a brief time and the temperature of the diverter components rises, but not to the point where the material behavior changes significantly. In a long pulse plasma, the diverter reaches thermal equilibrium. The temperature of the material stabilizes at the value determined by the balance between the incoming heat from the plasma and the cooling system carrying heat away. At this equilibrium, material properties such as thermal conductivity and emissivity may be different from their room temperature values, and the erosion behavior of the diverter surface changes. These effects, which will dominate the engineering of a real power plant's plasma-facing components, only appear at long durations. The East team's ability to maintain stable plasma operation for 1056 seconds, with the diverter operating at its thermal equilibrium condition throughout, means that the diverter design and materials choices are validated at the timescale where the relevant physics is actually happening. The 1056-second result is a scientific milestone. It is not yet engineering proof of a power plant. The gap between what East demonstrated and what a commercial fusion power plant requires is real, significant, and worth being honest about. East produces plasma at conditions sufficient to sustain fusion reactions, but it does not produce more energy from fusion than it consumes in creating and maintaining the plasma. The Q value of East, the ratio of fusion energy produced to energy input, is significantly less than 1. East is not a power-producing machine. It is a research machine designed to study plasma physics, and its plasma parameters, current, temperature, density, are optimized for achieving long duration, not for achieving high fusion energy output. The next step in the fusion development chain, the step that closes the gap between research and power production, is ITER, the International Fusion Experiment under construction at Cataract in southern France. ITER is designed to achieve Q equal to 10, producing 10 times more fusion energy than the energy put in to create the plasma. It is a far larger machine than East, with a plasma volume approximately 10 times larger and a magnetic field significantly stronger. ITER is expected to achieve its first plasma in the late 2020s and its full fusion power experiments in the early 2030s. China is a participant in ITER and has contributed components to its construction. But China is also developing its own next-generation fusion device, the China Fusion Engineering Test Reactor, CFETR, which is planned as a bridge between the scientific demonstration that ITER will provide and a commercial demonstration fusion power plant. CFETR is designed to demonstrate tritium self-sufficiency, the ability of a fusion reactor to breed its own tritium fuel from lithium in a blanket surrounding the plasma, which is essential for commercial fusion power because tritium does not occur naturally in useful quantities and must be produced within the reactor itself. The timeline for these devices is measured in decades, not years. ITER will not complete its scientific program until the 2040s. CFETR, if funded and built on the schedule currently planned, would demonstrate commercial-scale fusion power in the 2050s. Commercial fusion power plants, if the technology continues to develop as its proponents expect, are most plausibly a feature of the second half of the 21st century. This timeline is often cited as evidence that fusion is still the perpetually deferred technology. But it is worth examining what the timeline actually represents. 60 years ago, sustained fusion plasma of any kind was not achievable. 30 years ago, plasma durations were measured in seconds. Today, EAST has demonstrated 1056 seconds of sustained fusion-relevant plasma. The progress is real, it is documented, and it is accelerating. The question is not whether fusion is possible, the physics is clear. The question is how quickly the engineering can be solved and whether the funding and political commitment to solve it will be sustained. While the government-funded international fusion program has been advancing steadily, a parallel development has accelerated the timeline conversation significantly. Private fusion companies have entered the field with levels of investment and ambition that would have seemed implausible a decade ago. More than 30 private fusion companies are now operating worldwide, backed by a cumulative investment that exceeded $6 billion by 2024. Several have claimed timelines to demonstration plants that are significantly shorter than the government program, some targeting the 2030s rather than the 2050s. The approaches vary. Some use tokamak designs similar to East and ITER but with high-temperature superconducting magnets that allow smaller, more compact devices. Some use entirely different confinement approaches including inertial confinement, stellarators, and field-reversed configurations. Commonwealth Fusion Systems, a spin-out from MIT, has built and tested high-temperature superconducting magnets that achieve field strengths significantly higher than conventional superconducting magnets, which would allow a tokamak to achieve the plasma conditions needed for Q greater than 1 in a device much smaller than ITER. Their demonstration device, SPARC, is under construction and aims to demonstrate Q greater than 2 in the early 2030s. If Spark achieves its goals, it would compress the fusion development timeline significantly. Helion Energy, backed by significant private investment including from Microsoft, is pursuing a different approach, pulsed fusion using field-reversed configuration plasmas, and has signed a power purchase agreement with Microsoft for fusion electricity delivery in the early 2030s. The agreement is contingent on Helion demonstrating that their technology works, but the existence of a commercial power purchase agreement for fusion electricity represents something genuinely new in the history of the technology. China has its own private fusion sector, smaller than the international one but growing. Several Chinese startups are working on compact tokamak designs and alternative confinement approaches, supported by a combination of private investment and government research programs that allow closer collaboration between the private and public fusion sectors than exists in most other countries. The significance of the private fusion sector for the East result is indirect but real. Private fusion investment has raised the global profile of fusion research, attracted talent from adjacent fields, and created commercial pressure on the timeline that the purely academic government-funded program did not face. The combination of EAST's 1056-second result, demonstrating that long-pulse plasma is a solved problem at the physics level, and the capital flowing into private fusion companies targeting the 2030s, has created a moment where the question of when fusion power will arrive is being asked seriously in ways that it was not a decade ago. 100 million degrees, 1056 seconds. A plasma 7 times hotter than the core of the Sun, held together by magnetic fields, producing the same reaction that has powered every star in the universe for billions of years, sustained long enough that the relevant physics, impurity accumulation, diverter thermal equilibrium, steady-state current drive, could fully develop and be demonstrated under control. This is not fusion power. The machine in Hefei does not produce more energy than it consumes. The power plants that run on this physics are decades away. None of that is concealed in the result. What the result is, honestly, is the clearest demonstration yet that the engineering path to sustained fusion plasma, not the physics, not the theory, but the actual control of an actual plasma in an actual machine, is being walked successfully, one step at a time, faster than before. Fusion has been 30 years away for 60 years. The question is whether the work being done in Hefei, in Cataract, in the laboratories of a dozen private companies, is evidence that the 30 years are finally actually 30 years, or whether the horizon keeps moving. I want to know what you think. If fusion power becomes commercially available in your lifetime, if the reaction that powers the sun is generating electricity in a plant somewhere on Earth before you die, what does that change? What problem does it solve that nothing else can? Drop your answer in the comments. Every single one gets read. Hit the like button if this changed how you think about energy. Subscribe to Addy Mel for the stories that matter before they make the headlines. Turn on notifications because next week we go just as deep on something just as real. The sun burns at 15 million degrees. The machine in Hefei burns at 100 million. And it held for 1056 seconds.